last 1.5 hours. I'm going to talk about two papers. One again published, the other one is still in the publication process. We submitted the revision to JET and hearing back and being back on that. So the first one is going to be like a multi-unit options. The title is a near Pareto optimal option with budget constraints. So the motivation for this is actually like two sides, right? So this is going to be multi-unit and budget constraints. And the issue of budget constraints is, of course, it has been studied, but not studied as much. So in the first 4 chapters of BJ's book, I covered most of the material, but actually there were some things that I had to skip due to time constraint, and there was some discussion about like budget constraints with single unit auctions there, and then there are some like some results on this. But budget constraints are relevant, especially when the objects are of high value and the single buyer getting all the items, and the motivation actually is come from the online advertisement auctions, right? So maybe from your like some classes that you are familiar with the generalized second price auction mechanism of Google to sell advertisements, like why this is a very practically important question, because basically billions of dollars of revenue is generated by these online ad auctions used by Google and Facebook and other companies, Bing, and the idea is basically that now it is changing, by the way. No-click internet is coming, so all these things will need to be restudied again, because people are using like stuff like Google less and less, and then only using either the AI tools or AI generated answers from the web pages such as Google or Bing, and there is less clicking going on. So therefore, like the advertisement models needs to be changed, but it's a question of the future. Up until recently and in the recent past, the issue of selling online advertisements was very important. But most of these papers, they also did not consider an important aspect of this setup, which is the budget constraints, right? So basically, if you want to give advertisement to Google about selling your product, they ask for 2 things. One of them is, what is your like per click value that you are willing to pay? And then what is your weekly budget or daily budget? So they basically use your input in the instantaneous auctions that they run every time somebody does a query, a search. But when your budget is exhausted, you are not there anymore, and then they use the remaining ones, right? So this was not that much studied, and we basically start with this. So we wanted to understand multi-unit auctions with linear demands and budget constraints, motivated by importance of this problem in the online advertisement space. Okay. So what is our model? There are m units of the same item to be sold. This is not a multi-unit auction. I'm sorry, multi-item auction. It's a multi-unit auction. There are m units of the same item. There are n bidders with private values VI and private budgets VI. So they have both 2-dimensional private information, value and the budget. And we also assume that the budget constraints are hard. So they cannot simply afford paying more than their budget. So if a bidder gets 2 units of the item by paying P, so we assume linear demands. So like the utility will be under 2 contingencies. If the total price is less than the budget, it is just like this function. So I get 2 units, my per unit value is VI. So Q times VI is my utility from the allocation minus P, which is the price. And if If the price is greater than PI, then I get a negative payoff. Right? So I cannot, like, basically I cannot afford to pay more than PI. So it's a hard budget constraint. Of course, you can think about like a little bit soft budget constraint, something like, for instance, if I had to pay more than PI, then I would need to go and borrow this, and I need to pay interest. So there is this additional like a burden and stuff like that. That would be like more like soft budgets. But here we consider a hard budget. And another important thing is the equilibrium concept that we consider is like ex post Nash equilibrium. So we do not consider Bayesian Nash equilibrium. And this is coming from basically the motivation that, like in the online advertisement, for instance, like the Adam Ostrowski-Strauss or the variant paper, they also consider different equilibrium concepts rather than Bayesian Nash or perfect Bayesian, because of the situation that basically you can change your bit at any time. So it's like you more like a stable allocation is more appropriate than like a single shot equilibrium of the game. Yes.
So what's the auction format again?
The auction format is going to be like we are going to propose an auction format. So this is like more like a mechanism design problem. So we are not fixing the, like we are not saying that we are considering discriminatory or uniform or some other auction format. We are going to tell you that here is an option that could work well. Okay.
So if we finite, looks like feature finite.
Yeah.
Right. Does it make any difference? Why?
So the difference between infinity and so I think like this would make a difference if we have a probabilistic setup, right? So like for instance, if you have some probability that you will have to pay more than C, if this C is negative infinity, that will make it no, this is never be the case. Whereas C is finite means that this is okay because of taking condition expectation, but in our model it's going to be ex post Nash equilibrium, and there is not going to be any uncertainty, so it doesn't really matter. Yeah.
Well, if things are very small, then sometimes it's better to exhaust budget.
Yeah, we will actually exhaust budgets. Yes.
Even like if I spend more than my budget, that might be better for me. Right? If fees are really tiny.
So you will see, like basically, like I'm going to now like first tell you some impossibility result that was proven before us in terms of getting the truthful revelation of the budgets and getting full efficiency. So we will not be able to go there, but then we will talk about basically what are the strategies, and our main basically contribution will be that here is a mechanism that doesn't get to full Pareto optimality, but it gets to near Pareto optimality, and it has nice incentive properties. So we are not really like solving a pure mechanism design problem in which like we try to maximize something, but it is just like a mechanism that works well under some circumstances. And for those arguments, I don't think basically what happens is they will exhaust their budgets, but they will not optimally choose to use more than their budgets. They prefer to be in their budgets.
I see.
Yeah.
So
all the full, okay, so you will see like maybe, yeah.
you can tell me, so the issue of budget constraint seems to be relevant even if there's only one unit of item to be sold. And is there something specifically you want to talk about in terms of multi-units, or is it more like generation or
Yeah, so like M units and they will have budgets, right? So M is allowed to be 1, but this can be done for arbitrary M without requiring to be 1. So I'm not sure, like for instance, if the negative result that I will tell in the next slide in the proof they require M to be multiple or not. But basically our mechanism does work for arbitrary M specified. So let's continue. So we are interested in like a semi mechanism. So like when you say maybe this is like more like a market design rather than mechanism design. So what's the difference between mechanism design and market design? Mechanism design is mostly like in a more abstract setting, find like the optimal one using this equilibrium notion or that equilibrium notion, whereas like market design is sometimes maybe you will not solve for the optimal, but you have so that there are some good properties that is lacking some other properties. So we are doing a market design question, designing an allocation and pricing rule with good revenue and efficiency properties. Okay, so and the starting point of this paper is basically a computer science paper, like recently published at that time that we started working on this problem. Basically, what they show is that in this setup, that the same setup that we consider, there is no truthful and Pareto optimal mechanism. So if you want to get Pareto optimality in terms of maximizing social welfare, there is no way you can get that with a truthful mechanism. Okay, so knowing this impossibility, we know that it's not going to be possible to do that, but we can still get something good. And we introduce a mechanism that we call weekly bid budgets. So it's going to be basically like in the normal setup, it's going to be exactly like the William Vickrey's idea, like a second price auction idea. But with budgets, it's going to be slightly different and it will have nice incentive properties. So it's not going to be truthful. As you will see, like in a minute, that there will be some kind of lying, could be beneficial. Okay. But the nice thing about our mechanism is going to be that whenever, so this is basically, you know, the main thing, the main takeaway will be that whenever the lying is beneficial, it's also helping the auctioneer too. So like if you then consider an equilibrium of this, okay, and compare it with truthful revelations, the equilibrium of this is going to be even better for the auctioneer. Yeah.
Here type means the pair of the variation.
Yes, yeah. So the type is two-dimensional, value and budget. So misreporting is beneficial to a bidder only when it increases the revenue to the auctioneer. So that's why we think that this is like a good mechanism, and it will have like like I will explain this in a moment. So this is about like the revenue properties, but what is the efficiency property? Efficiency property will be that like full Pareto optimality will require that all the bidders who get a positive amount of this good should have higher values than the bidders that did not receive the object, right? So we will have this as near Pareto optimal, because what we will be able to show you is that we have three kinds of bidders. We will have like a full winners, like who actually exhaust their budgets. We will have full losers who don't get anything, but there is going to be like a partial winner, because of like we actually, I forgot to tell you, we assume that this is m units, but this is divisible. Okay, so there is going to be a bidder who is ranked at the middle, who may potentially not use all her budget, and given basically we will be able to show you that all the full winners will have higher values than all the full losers, but this person who is in the middle may be the wrong person. Okay, because of the one incentive about the line. But this is like kind of like a preview of results, but let me go a little bit slower. All right. So I need to first tell you what our mechanism is. So the mechanism is we will take the vectors BV, so they will each of these n agents will tell us their private budgets and private values, and we will rank them in a non-ascending way in terms of their values. The highest value, second highest value, third highest value. Like the highest value person may not have a high budget, right? So, but we only rank them with the values only. Then we will calculate the unique, what we call a cut point C prime, according to the following pricing function. All right. So, so we will like, this is V1, this is V2, this is V3, this is V4, this is V5. Okay. So let's say that this cut person is V3. Okay. So the pricing is gonna be like in what's the idea of weekly pricing? Like think about second price auction with single unit auction, right? So how much do you pay is that you pay the highest losing bid, because basically you pay for the externality that you exert on others. So if you weren't there, then the other person would have gotten it, so you have to pay that much, right? So it will have a similar idea, but what we will do is that for the full winners,
So
Yeah.
what is the size of this circle
so
here?
like these are representing the budget. So like this length is budget. Sorry. This length represents the like this length is the B1, this length is B2, this length is B3, this length is B4, and this length is B5. Okay, so it is a simple idea. So for the full winners, what are we going to do is, so like this is the partial winner who is using this part of the budget to buy the items, and this part of the budget is unused, right? So what are we going to do is, like, let me actually use maybe different colors. So this is the unused budget. Okay. So for V1, what I'm going to do is that for the first this length of the budget, I am going to charge V1, V3. Okay. And then for the budget of V4, okay, this one, I'm going to charge for this part V4. And lastly, for like the rest of this here, like for the V5, I'm going to, for this part of the budget, I'm going to charge V5. So basically, I'm going to, for all the full winners, I am going to use the same pricing system up to their budgets in decreasing order. For the unused part of the shortcut bidder, use the value of shortcut per item, then V4 the same and V5 the same. This is the pricing rule for all the full winners. And for the, I really cannot use this. It doesn't make sense to use this for the shortcut bidder, because if I do that, then I will be actually charging his value for the unused part. So the cut for the cut bidder, it doesn't start from the red part, but it starts from the blue part. So for the bidder who is at the cut level, the pricing is different. The pricing only includes from the highest losing bidder's value. Okay, but for all others, also this part is also used. So this is the definition. This is how the pricing works. Yes.
So can you explain again, how many units do these winners win?
Yeah.
So given
So,
some
Yeah,
people
so
are-
that is the good question. So like from this, you can actually also see that there is going to be a unique cut point. So there is going to be a unique bidder and a unique used part and unused part of this unique bidder's budget in order to make sure that exactly M units are allocated, right? So if this cut point goes to the right, then there will be more and more bidders, more and more units will be allocated. Because first of all, everybody's per unit prices are weekly decreasing, right? And for the same budgets, they are allocated more and more items. And secondly, the number of winners are getting larger. So there's going to be it's very easy to show that there's going to be a unique cut point given this pricing rule.
So again, so the cut, are you saying the cutoff is decided in such a way that according to your pricing rule,
Yeah,
the
exactly. M units are allocated.
the first person
Yeah.
will
Exactly.
buy the
So
unit
this
that
is
is
math.
equal
So,
to.
okay, so the first person's, the number of allocated items is like, let's say, like this is gonna be, let's call this like B3U, which is the unused part. So it's gonna be the total number of items allocated to bidder one is B3U divided by B3 plus B4 divided by B4 plus, you know, like let's assume that this length and this length is the same. It doesn't have to be, but B5 divided by B5. This amount of this unit of goods will be allocated to bidder one. And similarly, we do the same for bidder two and bidder three.
Okay, so which is to say, am I right that let me see if I understand. So are you saying that is
It is the total number of units allocated to bidder one.
I see. And that's it. Sorry, does it equal to if you get that that unit, then how much does the first bidder pay in total? I got a bit confused.
So okay,
And
so
is it within his or her budget?
yes,
Or,
yeah. Like
how-
he's going to pay the whole budget.
Okay, so you're saying that the first.
The value in this
I see.
is equal to V1, right?
I see. Are you saying that these first units are totally charged?
Yeah.
He or she is charged
Yeah.
value equal to V3,
Yeah.
and the number of units is this given by this,
Yeah.
and then these numbers are decided in such a way that actually the sum is going to be equal to the budget.
Yes, exactly. Yeah,
Okay.
everybody will be like full winners, they pay the full budget. And the cut bidder will be paid like some portion of the budget. And the thing is that there's going to be a unique cut point.
I see.
Sorry, how much if agent two getting?
How much?
Does agent two get?
Agent 2 again the same. So like it's gonna be B3 divided by, but basically since this length is greater than this length, the B2 will get like B2 divided by V3 amount of the good and will pay. So like if this length is greater than this length, then the whole thing is gonna be red, right? So I'm gonna be only charged V3
I see.
per unit.
And how means for making the
So we assume divisible, perfectly divisible goods. So like there are n units, but they are divisible goods. No integer problems.
So given the order quasi-linear setting.
Yeah.
And the linear, if I understand the utility linear in the units of consumption.
Yes, that's right. Yeah.
Does it mean that actually your mechanism could be done for the individual case by randomization? Do you know whether?
Yeah, I think for that one, we may need this like C being negative infinity. We didn't formally do it. Like you can also think about this like share options of Wilson, right? So share options is like also like Wilson has this like a for the perfectly divisible case. So I see more similar to like the Wilson's share option. We did not really think formally about randomization and signal unity.
I see. The impression is though that
Yeah.
you can still pay the.
So here like n doesn't appear anywhere, right? So you can even normalize n to be 1. Right?
Right,
So,
right,
yeah,
right.
yeah.
Yeah, my impression that you can.
Even perfect divisibility.
And then that makes budget to be never violated, but then the goods are sent to be still random and then the utilities seem to be the same, so I thought that might work.
Yeah, could be. Yeah, you are right. All right. So so now you understood the pricing rule of the mechanism. Now like the first result is that, so this is like a VQ auction. Like VQ auction, like think about, for instance, like a generalization of VQ auction for multi unit case to the uniform price auctions, for instance, right? Uniform price auction, like at least in the like single unit demand, it works. And the idea is basically everybody's charged the highest losing bidder's value. Here we are kind of adjusting for the budgets, and we are just saying that like these budget lengths are kind of incorporated into the budget conflicts, right? So it is similar, and the first result is that the value increase budgets or value increase values, then this revenue in this mechanism, assuming truthful revelation, is going to be increasing. And now,
Sorry, everyone's budget is almost very, very large. What happens?
that one, okay, so that everybody, so here, every full winner will be charged the highest loser's value, and I'm sorry, every full winner will be charged the lowest winner's value, and the lowest winner will be charged the highest loser's value.
So it converges to the uniform price.
Similar, right? So it's not exactly identical, right? Yeah, because like uniform price also.
so the first bidder gets everything.
Oh,
Right.
Oh, okay, sorry. Yeah, the first winner will get it.
Then
Yeah.
are they charged second highest?
Yes.
bidder?
I forgot about that part. Yeah, good point. All right, so let's continue. So now we have some results about the incentives under this mechanism. And our first result is that, so since we have two-dimensional private information, right? So we have B and V, and we can either B can go up or down, and V can go up or down. So there are four potential, like at least weak to go up, weak to go down, weak to go up, weak to go down. Four things that we need to consider. And the first result is that for the cases in which the revenue can go down, which is only V goes down, B stays the same, or B goes down and V stays the same, or B and V both go down, these are never best responses. These are dominated by truthful bidding. Okay, so actually there are 9. Right? So there are not 4, but 9 cases. Other than truthful revelation, I have go up, go down, and stay the same. Go up and go down, stay the same. 3 times 3 is 9, and there are 8 deviations. And among these 8 deviations, 2 of them are clearly revenue decreasing, right? Under reporting value, or under reporting budget, or under reporting both of them. They are weakly dominated by truthful reporting, so they should never happen in equilibrium. Now we are done. Out of this 8, 2 of them we are done with, right? Now let's consider the other options. The first one is we can show that understating the budget and overstating the value, which may increase or decrease the revenue, because it's not going in one direction, right? So from the previous lemma, we know that high values or higher budgets are better for the revenue. So for these 2 cases, it's not clear. The effect is not clear, but we can say that in one result, the first one, understating the budget and overstating the value, cannot be in best response. It can be in the set of best responses only when bidder's I's utility in her best response is 0. Okay, so this is what we can show. What does this mean? This means that if basically once you if you do truthful revelation, you will never get a negative utility. All right, and with this fact, this would mean that B minus B plus is not a good strategy, because if you do that, then your utility will be 0. Okay, so this kind of also, in a weaker sense, not a weak domination sense, but in a weaker sense, shows that this deviation will not happen. Okay.
I have one question. So about the misreporting of
Yeah.
the budget.
Yeah.
So suppose that I have just 1 million yen,
Yeah.
but I misreport that I have 2 million yen.
Yeah.
And so then I'm charged 2 million yen.
Yeah.
So which exceeds my true budget.
Yeah.
So then what will happen?
Then you will get negative C.
Oh, I see. Oh, I see.
Yeah.
Okay, I see.
So the other one is the other thing, that is B plus B minus, and our next result is that B plus B minus brings a higher utility than truthful bidding. Then the auctioneer's revenue with B plus B minus is lower than is not lower than the revenue with BI. So basically, this proposition 7 establishes that overstating the budget and overstating the value can happen, and this of course will not happen for the full winners, right? Because they don't want to do that, but this could happen for the shortcut, the cut bidder. This could happen, but when this happens, the revenue will be high. So when we combine all these 3 things, we call this like a big refined equilibrium, and our main result is that in a refined equilibrium of our mechanism, revenue is bounded below by the revenue of weekly budget with truthful revelation. So we say that the truthful revelations is not necessarily an equilibrium, but in the ex post niche equilibrium of our mechanism, the revenue will be higher than the truthful revenue. So it's going to be actually helping the auctioneer in terms of the revenue. Okay, that's our first result. And the second result, as I mentioned earlier, is related to the efficiency of this mechanism. So again, as I told you earlier, what does the full efficiency require? The full efficiency requires that all the budgets, all the bidders will be ranked in terms of their values, and the winners should have higher values than the losers. That's what efficiency requires. So we don't get to that fully, but what we can get is the following. All the bidders who are the full losers, full losers, will have lower values than all the bidders who are the full winners. But this doesn't necessarily mean, like, for instance, I can have, let's say that these values are, 6, 5, 3, 4, and 2. This is not fully efficient, right? Because, like, if a guy with value 4 is not getting the item, although a guy with value 3 is getting at least part of his budget is used to get the item. But this 6 and 5 is greater than 4 and 2. So it is satisfying this. The reason is basically that one of the lower value bidders in equilibrium can come and become the shortcut person. So the cut bidder. Okay. So it's not fully efficient, but it is near efficient in the sense that the full winners have higher values than the full losers. But this cut bidder can be not in the correct order. So this is our second result. And then we actually, I think it's not in the published version of the paper because they wanted us to take it out. They wanted to make the paper shorter, but this was in the working paper version of the paper that we also compare our mechanism to a more standard mechanism. So think about like a market clearing price mechanism. It's a very simple mechanism here, right? So like just find the market clearing price and charge everybody whose values are higher than this market clearing price, that price. Okay, and so they are selling all these items to all interested bidders at a fixed price. But if you do this mechanism, the first thing that you can see is that overstating the budget or value is weakly dominated by bidding the true types. Okay, and we show that basically when you compare, like that mechanism also in the context of private information with values and budgets will not result in like full efficiency and truthful revelation, but just ignoring the incentives here, we have a result that shows that the market clearing price mechanism, the difference between the market clearing price mechanism and our mechanism is at most the highest of the budgets. So that's one more result. And some similar results. So I'm going to, I think, like just conclude here to make sure I have enough time for like a little bit more time for the other paper. And to conclude, this mechanism that we propose is in the spirit of weaker options, in the sense that the values, the per price charging of the bidders are determined by the losers' values and budgets. Okay, it doesn't have the full truthful bidding as a dominant strategy, but it has some nice properties about the deviations. The deviations can happen, but it only happens when it benefits the auctioneer with the revenue compared to truthful case. And we get near Pareto optimality in the sense that only one bidder may be out of its place, and that's the cut bidder. And that's it.
So, anyone has often said that the budget constraint should be only in one direction. Like, so I cannot say I am a millionaire, but I can say I'm,
Okay.
yeah, my income.
Yes.
That's your conclusion.
A good question. So, like basically, there is some kind of like a verification device in which you that prevents me from overstating the budget.
Right.
Understating is fine. Yeah, understating is fine. I'm not sure. That's a very naked question, and I'm surprised that we did not think about this problem before. But I'm not sure. Like, I think the whole paper cannot be written with that assumption. There is some bite in terms of assuming that overstating is a possibility. But I need to think. Any other questions? Yeah.
Could you remind me, what we know about the 50 unit demand?
So for the unit demand here, right? Unit demand with budget constraints or without?
The unit demand with budget constraint, the M items on sale. Can be the.
I don't think there are. I'm not aware of like without budget constraints, right? So like okay, so let me like for the without budget constraint case with single unit demand, like discriminatory price option is a efficient equilibrium. Uniform price option has an efficient equilibrium. You know the equilibrium there, but I don't think we know an equilibrium characterization for arbitrary budget constraint, especially when the budget constraints are private information. So I think the Lobzinski law in some paper is the one that allows for this like the constant marginal utility model. But I'm not aware of any papers that looks at this like single unit demand, multi-unit options budget constraints. Maybe there are papers, but I'm not aware of it. So we don't know. At least I don't know.
Sorry, I have listed.
Yeah.
In the existence of equilibrium currently here,
Sorry?
is the existence of the.
No, we do not have assumptions. Yeah. So like we didn't like when we are working with examples and stuff, we did not face any problems with existence. So we conjecture that equilibrium exists, but we do not formally prove that an existence of the equilibrium.
Yes, in the auction case, usually we have all sorts of discontinuity.
Yeah, but I think for those things they are more like in the Bayesian setup. Here, like expose is a little bit easier, but like I don't think in the paper we have established an existence result. Yeah. All right, so now let me move to the second paper. I have about 45 minutes, which is good. So, but by the way, I forgot to tell you, the first paper was co-authored with Ravi, who is an our professor at CMU, and Emin, who had gotten his PhD from Carnegie Mellon and worked at marketing department for a while before he moved to Amazon as a senior researcher. And this paper is co-authored with Onur. I think this is Onur's first ever open paper, Katya, and my PhD student Song. And the title is When Speed is of Essence, Perishable Good Auctions. Continue. So there are like perishable. What do I mean by perishable goods? There are many examples, like fish. Tokyo Fish Market. What was the name? I forgot. What's the fish market name?
And the
Fish market, I think, is one of the largest in the world. And Sydney's fish market is actually the largest in the southern hemisphere of the world. So yeah.
So a year ago, the fish market moved from Tsukiji to Toyosu. Another
Oh,
place.
yeah.
Maybe it still could be the largest now. I don't know.
So yeah, like many. I think the first time I came here, one of the first things that we did in Tokyo was to go to the fish market. It was in Tsukiji then, many years ago, and then have fresh nigiri and sashimi for breakfast. It was like so good. Anyway, so fish auctions is one example, but there are other examples like meats. Sometimes like large amounts of meat is sold via auctions. Flowers. We actually have another paper about flower auctions, which is if I have time, maybe I can talk about it. And like all these auctions, they have large amounts of the good that needs to be sold in a short amount of time. So it's not the case that they actually will be rotten in 1 hour or something, but they have large amounts of fish that needs to be sold that day because those are fresh fish, right? And then they are like sold sequentially, okay? And there are different auction formats that are used, but speed is always very important. And this is not actually even just for the perishable goods. So like if you have many items for sale, the speed of the auction is very important. I remember back in the US, I once went with a friend to a used car dealership auction in which thousands of used cars, they come and then like they bring the car and you only have 10 seconds to sell the car. They like people go around checking whether there has been any accidents or something with some devices and stuff, and they like you cannot even understand what the auctioneer is saying. And this doesn't take more than 30 seconds because in at most 30 seconds the next car will come. So like the speed of the auction is very important. So it's not due to really the perishability of the good, but more like the number of items to be sold is so large. Okay. And some fish markets use the descending price auction. As far as I know, like the Japanese fish market, they use some kind of like an English auction, right? So it's like the prices are increasing. But many fish auctions actually, especially if they have an electronic system, they actually use Dutch auction. So like similar to the selling of flowers in Netherlands. So they have, for instance, like in Sydney fish market, there are they have an electronical system in which they have clocks A and clock C, and these are used. These use pure Dutch auctions. The price starts from high and goes down up until somebody pushes the button, and then this person who pushes the button will have to pay that price and will decide how many lots of fish they will get, and the remaining fish is again sold with the remaining ones. And this is like a standard Dutch auction, but it's also like a sequential auctions because these are typically used to sell fish that has multiple quantities are available. So like, more standard fish, they have 20 boxes of the same thing. Whereas they have this Club B auction, which is our main, main motivation and main model and choice here. They use it to sell premium seafood, like sashimi grade tuna or live lobsters, and they don't actually have multiple boxes of the same thing. They like individually sell these items, right? So for instance, like in in the fish market here, like these big tunas are sold via auction and it's one by one, right? And then in Sydney, they use this unusual auction format that I will tell you right now. So, and the same thing is used in Honolulu in the US to sell fish. The difference between Sydney and Honolulu is that in Sydney there is like an electronical system, and in Honolulu they use a verbal auction. Okay, so how does this Sydney Honolulu auction that we consider in this paper work? It works as follows. So rather than the price starting from a very high price, like in a Dutch auction, or very low price, like in an English auction, actually the price starts from a middle ground. Okay, and if anybody is interested at the price, at the starting price of the auction, then the auction becomes English. So it starts going up. If there are two or more bidders that are interested in the item, it continues going up until the point there is only one interested bidder left, then the auction stops. So it can immediately start as an English. But if nobody is interested at the initial price, then the price starts going down. Okay, so it starts like being like a Dutch auction up until the point when somebody says, I'm interested. Okay? But at that time, other bidders would have a chance to jump back in and say that I'm also interested, and then it can become an English auction. So there are three possibilities. Pure English, like let's say that the auction price starts from 50. 50. It can just immediately start going up, that's the English. Or it can go down from 50 to 30. And at 30, somebody stops and nobody's interested in increasing the item anymore. So that's sold at 30. So this is pure Dutch. That's the second option. And the third one is like it starts from 50 and goes down to like 20. And then some people say I'm interested and it goes up to 40 and stops there, for instance. This is another possibility. So like Dutch and then English. So three options, either English only or Dutch only or Dutch and then English only. And this auction method is used both in Sydney and Honolulu. So this was an interesting auction format that we observed. And so this is like a description of what I just told you. And importantly, in practice, both in Honolulu and Sydney, all these three things are observed. So they all happen. So it's not the case that these are possibilities, but only one of them happens, for instance. They all happen. Okay. And another important thing is that, let's say that when the Dutch phase starts, in practice, you actually do not see the prices to go like near zero or very low values. They actually bid, like jump. The first person, we call it like jump or pushes the button, say I'm interested, at strictly positive prices. Okay? They do not wait till the price goes to zero. Okay? So because of that, we have some discussion here to motivate that we need like to expand our theory a little bit in one dimension and in a particular dimension. So this part is very important, right? So like when the starts going down, when somebody pushes the button, that's not the end of the game. You can always say that I'm also interested, and then the price will start going up again. So there is no real trade-off when let's say that the price is going from 50 to 30. Is there any reason for you to stop the clock at 30? If there is no like time cost, even when you consider like risk aversion, loss aversion, regrets, whatever, like other behavioral factors, there is no cost of waiting because you can always let the price go all the way down to zero. And if like just jump it, like if nobody jumps it till this point, you will get the price at the price of zero, right? And if somebody jumps it like 25, you don't lose anything because then you can say that I'm also interested, and then the price starts going up to 30. So basically, in risk neutral setup or risk averse setup, risk seeking, loss averse, regrets, all these setups cannot explain any behavior that makes the Dutch space stop at a positive price. It's like a dominated strategy to bid at a positive price. You can always later come back to this point anyway, so you are not losing anything. Okay? So because of this, we extend the model, like we basically consider an auction model in which bidders and the auctioneer, they care about the total duration of the auction. So because if they care about the duration of the auction, then that becomes a trade-off, right? So let's say that, you know, the price starts from 30, 50, and then at 30, you know that like this fish will never, like it's very unlikely that this fish will go less than $30. So if I just like wait, if we all wait and then, you know, jump in here and then, you know, wait for the price to go up to 30, then it's going to be like the same price, but the auction will take longer. And it is costly for the auction to take longer. Clearly for the auctioneer, but also even for the bidders, right? So like basically this auctioneer wants to, I'm not saying like, you know, there is a huge difference between, you know, 50 seconds and, you know, 90 seconds. But I'm saying that if it goes from 50 seconds to 100 seconds, for instance, then the total duration of the auction will become like 10 hours rather than 5 hours, which will not be feasible, right? So, and also similarly, the bidders are there. They are professional bidders who actually would like to get, you know, cases of fish. So they also care about the time. So that's why we actually add basically a discounting function in terms of the total duration of the auction and solve the equilibrium of this hybrid auction that we call Sydney Honolulu auction and compare this equilibrium to the Dutch auctions. And then we have some analytical results, we have some numerical predictions, and then we take this the same design to the lab, and then we do the experimental lab, you know, both in Sydney and in Honolulu, because our actually quarter is from Honolulu, like the University of Hawaii, Honolulu, and then we have some results. So, any questions?
And these auctions in reality, so does the same bidder bid in multiple auctions? Because
That's right.
in your story, so if this auction happens the first thing in the
Yeah,
morning,
yeah.
then maybe I bid a
Yeah.
bit earlier so that it will be shortened by 30 seconds. Then I
So
stay until
this is like a very no, I agree. So if you want to have a like a good description of what's going on, I also don't understand. So like if you want to have a good description of what's going on, there is actually we have multi-item auctions, sequential. I'm sorry, not like sequential auctions, right? So they basically, but it is very difficult to model sequential auctions, even with like even in a much simpler setup. Like we have all these issues about you know the what do you call the declining price anomaly and many others. So
actually, my question is much simpler one, which is
Okay.
let's suppose that the bidder can be analyzed as if he or she participated in this one auction. However, in your story, basically, it seems that this bidder actually cares about shortening the duration of this
That's right.
particular auction.
Yeah.
But then if the bidder actually needs to stay until the entire day
Yeah.
for other reasons, such as maybe he or she actually needs to bid on some other auctions in the afternoon
Okay.
anyway,
Yeah.
then I wonder if to what extent it
Yeah.
actually
No, I agree. So this is like we basically this was like hard to sell in some, you know, for instance, publication chances. This was like really, you know, raised, and I can see the merit in this. So basically, you know, I think it's difficult to just like say that, you know, this really applies this single, like a single unit representation of this environment here applies. There are problems, but I think once what we want to say is that in an environment where the fastness of the auction is important, let's compare the fastness of the different auction formats. This is what we are doing about, and we are not really claiming that like this is like the representation of you know this you know Sydney or Honolulu fish auctions.
In the real world, are they only two instances or the some other?
So like we have another paper called Istanbul Flower Auction, and it's actually also a hybrid format, but different from Sydney and Honolulu fish auction. So in Istanbul Flower Auction, the auction is very similar. So it's either English if we have two or more bidders interested at the starting price, or Dutch if nobody's interested in the initial price. But the difference between flower auction and the fish auction is that in the flower auction, when somebody jumps in at the Dutch stage, then people have no chance of increasing it anymore. So that's used in Istanbul flower auction. And I think like if we do a little bit more search, these two are maybe used in a few other places. But like I think the majority is Dutch, like for the fresh produce.
There's no instance that this format is used for non-perishable goods.
So I am aware of like wine auctions, timber auctions, used car auctions. We did not see any.
I see.
We did not see any like hybrid formats. There are, I think, like it is theoretical. I think there is there was a paper that was interesting. So they have this like two prices going. One of them is going up, and the other one is going down. And then this is channel. I think it's called channel auctions. This is used. So in channel auctions, what happens is if you at any point, so like let's say that this is the time, so this is like time between 0 and 100. At any time, you can actually end the auction by agreeing to pay the price at this declining curve. This is Dutch curve basically. But in order for you to be present in the auction, you have to agree to pay this much. So this is like a similar idea, not exactly the same. All right, so let's continue. I have 30 minutes, it should be enough. All right. This doesn't work. Okay. Am I going? Okay. So the modeling choices that we have is we are going to have a private value model. I know that like people actually think about common value, especially in this context, in the sense that like the freshness of the fish is important or the quality. We agree that these are important, but since the participants in these typical auctions are almost all of them are experts, they really know like the quality of the fish or the trustability of the seller and stuff like that. So if there is a common value, but if this common value is also common knowledge, then you can ignore the common value and focus on the private value. And the private value here is like more like, I'm buying for my little fish shop, or I'm buying for this like my restaurant or my chain of restaurants. Do I need the demand for that kind of fish today? So that's the private value component. They are considering single unit auction model. I think I discussed this already. That there are like a sequential part of context here, but like for two reasons. One of them is simplicity. Other one is like when you, for instance, compare and contrast the clock A and C and versus B, like in clock A and C, you have multi-unit auctions. Like you have 20 cases of the same exact fish. And then Dutch auction is used there. But here we consider like premium seafood in which like there is each item is different. Like this fresh tuna is gonna be slightly different from the next fresh tuna, right? So that's why we consider single unit. And we consider like impatient bidders with linear, like with cost of delay. Basically, we are going to multiply the utility from the auction with a function that is inversely related to the total duration of the auction. That will come in next slide, and we are going to assume risk neutrality for simplicity again. So what is our model? We have n bidders. And the private valuations of the bidders are IID over 0 and 1 according to some distribution F. If the auction ends after t units of time at the price of P, the winner with value V will have a utility of the following. So it's like V minus P. So my value is V, I'm paying P, but this is multiplied by, like we consider multiplicative version for, again, analytical tractability. One could also think about like additive, but that is actually like much more complicated. So we are multiplying this b minus p with a function cb, which is decreasing in time. So the higher time it takes, the lower this value will be, and therefore lower the utility will be. And similarly, auctioneer utility is going to be just the price times the function that is a function of the total duration of the auction. We can potentially allow for CA and CB to be different from each other. In our like simple numerical examples, we are going to assume some kind of linear structure with different slopes. So we will still allow for different parameters. But like this is in general, like any kind of arbitrary decreasing function is a function of the total duration of the auction that is represented by T. We will assume that the loser's utilities are 0, and in the Honolulu auction, auctioneer chooses a starting price S. So basically, the auctioneer will do a maximization in order to maximize the expected utility. And remember now, since the auctioneer also has this utility from time, expected utility is not going to be equal to the expected price, right? Like here, like there could be allocative efficiency, like for instance, right? But the allocative efficiency will, for instance, will not necessarily mean social welfare maximization, because there is like a social welfare loss due to the time passing, right? All right, so let's continue.
CB is common knowledge.
Yeah, CA and CB are common knowledges.
So low attrition kind of.
Sorry?
Low attrition. Low attrition.
Board of attrition, I'm not sure if this is like board of attrition. It's like you would not, of course, they will take into account, but like, and you would prefer like a shorter duration to a lower duration, but it is not that, you know, like the person who like, you know, is deciding to give up late is losing something, right? So they are all on the same boat. So like more like in board of attrition kind of a situation, that you want to wait longer and longer is costly. But once you are, you know, once you leave earlier, then that's bad for you and good for others. Here, like this is, they are all on the same boat. They all want like this shorter duration. So there is a waiting game, but it's like a different waiting game than board of attrition. Okay, so let's say that. Okay, so like I also need to tell you about what's the strategy in different phases, right? So like for the Dutch phase, for the English phase, initially, right? So if you basically, I need to specify basically what time do you want to jump in, okay? And then if you jump in at the starting price, then you will be like asking for the English phase, right? And if you jump in after the Dutch phase starts, then that will give you kind of like a jumping time, depending on your value. But let's say that when somebody jumps in before you decided to do that, then you can potentially start an English phase, right? And since our utility specification is multiplicative, another simplicity of this one is that in the English phase after the Dutch phase, it is still a dominant strategy to leave till the price reaches your value, right? So let's say that like somebody, the price started from 50, you were thinking of, and your value is 40, and you were thinking of jumping at 20, but somebody else jumped at 30. Then, of course, then you want to say that I'm also interested, and you will increase the price till the price reaches your value. So like the English phase is easy to characterize. Due to this multiplicative formula, you would want to actually stay in the auction till the price reaches your value. But now the real question to solve is for the when to jump in. Okay, so let's consider a bidder with value V. What is the expected utility for various prices? So first of all, if you jump in at P and everybody else has values less than P, then you will get the item, right? Because nobody will increase the price anymore. So if everybody's value is less than P, this happens with probability f of P to the power n minus 1, then you will get the item, you will get V minus P, and you will also, there is a time cost. What is the time cost? The price started from S and went down to P. So the amount of time that passed the total duration of the auction is S minus P. So CV of S minus P times V minus P times F P to the power n minus 1 is your utility, indicates that the auction ends with the Dutch phase with your bid only. Okay. But there is another possibility, which is that somebody jumped in before you, but then you I'm sorry. Okay. There is the other possibility as follows. You jumped in, but somebody else also was interested in the item and kept increasing the price up until the time value, and then that person dropped out, and then you will have to pay that price. So that price, let's consider this to be X. So you jumped in at P, but some of the bidders have actually values higher than P, so they started the English phase after the Dutch phase, and then increase the price up until the value X. So that means the highest value among your opponents has a value of X, right? So this is like familiar from our Mondays class. So this is F1 of n minus 1X. So this represents the highest value among my opponents. So if the highest value among my opponents varies between P and V, let's denote this by X, then what happens is this was the starting price, S, right? And then it went down to P, you jumped in at P, but then highest value among your opponents will make the price go up to X and drop that X. What's the total duration? The total duration is this duration, S minus P, plus this duration, plus X minus P. So this duration is S minus P, and this duration is X minus P. So the total duration is S plus X minus 2P. Okay, so this is total duration of the auction, because it went down first and then went up first, but you need to add these up, right? So this, you have
Oh, yeah. So
Yeah.
are you assuming that the bidder chooses P at P of 0? Or are you assuming some kind of time consistency in terms of the
no, they basically like
discount?
you can. So you have to choose at time 0, right? Because like we allow P to be S. So I basically told you the whole story in which like P is smaller than S, but you can also jump in at S equal to like at the beginning of the auction.
So the P is the price at which I jump in,
Yes.
right? And do I choose that at time 0?
Oh, it doesn't matter.
But then are you assuming some is it just a discounting? I mean, it could be like
So like
simple discounting.
the utility is about total duration, right? So I'm incorporating the correct total duration of the auction. So like there is no difference between deciding to jump in at 30 when the auction starts, or deciding when the price reaches 30.
Okay, even if the C function is not a discount in the discounting form.
Without discount of.
Oh, okay. You mean like naive hyperbolic and stuff like that? No. We assume like.
So this is just a simple discount.
Yeah. So there is no naivete, or there is no other behavioral issues. Yeah. Sorry, I didn't get that. But it's like time consistency.
Another thing I wanted to ask is that, so the auctioneer chooses S, and if it goes to the Dutch phase,
Yeah.
then immediately after time 0, the auctioneer would have an incentive to lower the S, if it was possible, but like it's not allowed.
No. Like the auctioneer decides on S at the beginning. So
I know, but if it was possible for the auctioneer to reset S immediately after time 0, observing that it went to the Dutch phase, the auctioneer would have an incentive to
Yes.
But it's not,
Yeah.
it's not around.
Okay, so where was I? Okay, so I was explaining this. I hope this is clear. So we denote the optimal solution to this by PVS, and we would of course have like nobody will be jumping at a price higher than their value, and we allow for PVS to be equal to S. So basically, there is going to be kind of like a this P is going to be an increasing function with value, but we will allow for a pool at S equal to P is equal to S, right? So that could be a pool of players who all will jump in at the starting price. Okay. So then expected utility of the auctioneer is as follows. So we will only consider two contingencies. One of them is if the second highest value, so like here B represents the highest value and X represents the second highest value. If the second highest value is in between the jump price of the highest value, then the price is going to be just P, right? And then only S minus P amount of time would have passed. Second contingency is if the second highest value X has a higher value than the jumped price of the highest value V, then the price will first go from S to P and then will increase from P to X, and therefore this X minus the same, the X plus X minus 2P amount of time will pass. So this is the expected utility of the auctioneer. And here like G represents the joint density of the highest value and the second highest value among all the bidders. All right. So we have some theoretical results and then some experimental results. Some theoretical results are actually quite easy to see. Like the first one is that there is a theoretical possibility that all three things can happen. So in this equilibrium, and then in order to do that, actually it is enough to just solve a simple example like linear cost functions, uniform distributions, and then find out what the equilibrium bit functions are. It's going to be an increasing bit function with a pool at the S level. And then for different realizations of the bidders' values, you can have either both bidders, like for instance, let's say that the, for a specific example, let's say that we have like three bidders and the equilibrium bit, symmetric equilibrium bit function is something like this. So the values are increasing up to this point and then here after that. So if two or more bidders are here, then it's going to be an English auction. If no bidder is here, everybody is here, but let's say that the highest value is here, but the lowest value is very close to the highest value, then we will have a Dutch phase and then English phase, because the price that is chosen by this V is going to be smaller than X, so the Dutch and then English phase will happen. But where if the highest is here and the second highest is somewhere low, then the only Dutch auction will appear. So all three things can happen depending on the value realizations. That's the first result.
Guys, if you take CB, maybe if you take CB to rank 1, maybe uniformly, then do you have some continuity kind of thing?
So CP equal to 1 means that like okay, we will have some partial things to say, but if you are talking about both the auctioneer and the bidders have no time discounting, then we will have a revenue equivalence theorem. Basically, we will have like another thing that maybe I should have told you earlier is that revenue equivalence theorem doesn't apply here, because revenue equivalence theorem doesn't allow for the utilities to discount, right? So once you have like both the bidders and the auctioneer is not discounting, then the following is an equilibrium. So they all wait till the price reaches to 0, and then they all wait the English phase in which the price reaches to their value. This is going to be an equilibrium process.
So,
but like for instance, let me also add that's why, for instance, if bidders have no discounting, but the auctioneer has discounting, then the optimal starting price will be 0. Because like the auctioneer would know that they will wait till the price reaches to 0 anyway. So let me save some time and start the price from 0.
But yeah, in the first proposition,
Yeah.
looks like if all three occurs in for any CV, that is not exactly one.
Oh, okay. So we should we should add that this requires like a real time cost.
I see.
Yeah.
Okay.
Time costs are needed. Yes.
So yeah, if the auction goes to Dutch phase,
Yeah.
and the first person who press the button,
Yeah.
would have the highest within the
Yeah.
pay, right?
Yeah.
So is it so the situation where somebody else jumped in, so this person is basically indifferent between us.
You're right. Yeah, you're right. So like that's a good point. I should have told you this earlier. So like one can say that why do they even bother increasing the price, because they know that they will eventually lose, because like in a monotone symmetric equilibrium they like on the equilibrium path somebody jumped in before you necessarily means that that person will have a high value. We kind of argue this is like remember now we are in a single unit setup. It is a dominated strategy to basically give up earlier, right?
Right.
Dominated strategy.
So if they incur this utility from just being in the auction, then the story will be different, right?
That's right. So they are not. So their utility specification is the total duration of the auction, not total duration they spend in the auction. But like with that specification, although they are indifferent between just like not even engaging in English phase or dropping earlier than their value, we assume that they will be waiting till the price reaches to their value because it's a dominant strategy. Others are dominated. So like if other bidder is making a mistake, for instance, I could have been better off, right? Similar, like the standard argument. Okay. Second result.
Following up on the yield question.
Yeah.
Do you know whether you can say something about comparative statistics when you lower the time cost, something like that? So I guess you simply, so in the case in which is thought constant, then I guess you said that the optimal S is like 0.
Yeah.
So is there something which maybe?
So my guess is like we did not do that in the paper, but I think there could be some things that can be said. Yeah. We haven't done it like is a formal proof, but yeah, there are some like intuitive reasons why there could be some comparative statistics. Okay, so unless the bidders are patient, completely patient, which means like CB is equal to 1, the auctioneer's starting point is strictly higher than 0. So basically, but if bidders are completely patient, then you would want to start at 0. A patient auctioneer's optimal starting price is 1. This is also easy to see, right? Because like if I'm completely patient, if I don't care, and the bidders are patient, then the more I let them wait is better for me. And I'm not allowing starting prices to be higher than 1, for example. But these are not that realistic scenarios anyway. All right, so let's continue.
The optimum is for other auctioneers in between interior.
Yeah.
I see.
Yes, interior.
It looks like these propositions don't say that, but okay.
Okay. Yeah. No. I don't know if we have it in the paper. Maybe we didn't write it in the paper, but I think it can be proven. Okay, so let's continue. I have only 6 minutes left. So we can do more. We can actually have basically more or less like an analytical answer once we assume linear functions. So like compared to the standard like exponential discounting. Exponential discounting is more difficult to solve analytically. This is easier to solve, linear discounting. And then you can show that there is going to be kind of like a unique solution to an equation. And then you can actually give the jumping times, which is the bidding function in closed form like this.
But in this case, you have a time inconsistency problem, right? Because it's not exponential.
No, the exponential and the time inconsistencies are different, right? So like hyperbolic discounting and exponential discounting is like basically are for multiple decision makers at different time of the decision making, they have different rules, right? So basically, but the exponential discounting, as far as I know, is not needed for any, like time inconsistent preferences. So time consistent preferences does not, as far as I know, imply exponential discounting.
Let me see if I understand. So even if you have like a linear discounting,
Yeah.
if you are in the middle, like a time at t, then you're just discounting. Your discounting function may not have exactly the same.
No, but
format.
basically your utility, like overall the whole thing, like basically you don't really update on anything over time. Your utility from participating in this auction is just a function of the total duration of the auction, and it can be given in any decreasing form. It doesn't have to be exponential.
Okay, thanks.
So let's continue. And so Dutch auctions. So I told you that we wanted to compare this with Dutch auctions, but Dutch auctions equilibrium also changes once we have a time cost, right? So now, but let's consider a bidder whose value is B and jumps in at the price of P. This G is basically again f to the power n minus 1, which means if all of my opponents have values smaller than beta inverse of P, then I will get the object, and then like naturally in Dutch auction, we assume that the price starts from 1, right? So it's always that in Dutch auction, the price starts from the highest possible value. So from 1 to P, 1 minus P amount has passed. So this is gonna be in the linear specification. This is gonna be my time cost. And this results in a differential equation. And this is an ordinary differential equation with this boundary condition. Unfortunately, this doesn't have a closed form expression, but this is very easy to solve with numerical methods. And the auctioneer's expected utility can be written like this. So then we basically compare the Honolulu Sydney auctions versus Dutch auctions. And like let's start with a very easy case. Let's say that B is the discounting of the bidders and C is the, like for the linear specification, B is the discounting of the bidders and C is the discounting of the auctioneer. So I already told you that if the bidders are completely patient, then the seller is not patient, then the optimal starting price will be 0. And then Honolulu will become English, and then basically it just becomes like when you compare Honolulu versus Dutch, this becomes a comparison of English versus Dutch, right? And then since the bidders are basically completely patient, they don't have time costs. In terms of the revenue equivalence theorem will apply. But in terms of the auctioneer's utility, it's not utility equivalent. It's revenue equivalent, but not utility, right? So basically, like think about when you have only 2 bidders with uniform distributions, the expected selling price in any auction, standard auction, first price or second price is 1/3, right? But 1/3 is closer to 0 than 1. So basically, for low number of bidders, the total amount of time will be lower with English, but with high number of bidders, since the expected selling price will get higher and higher, Dutch will be better. So you can generalize this and you can say that, but this is not exactly the same because there is a little bit things going on here, but the basic driving force is that when you have more and more number of bidders, then the prices will be higher and higher, therefore the Dutch will have more advantage compared to, for instance, like the English. Okay, but of course, when B is not exactly equal to 0, right? Then the starting price doesn't have to be very low. That's the Honolulu will have an advantage of adjusting the starting price, whereas the Dutch will have the disadvantage of the price being fixed at 1. And this disadvantage will be less and less pronounced when you have more and more number of bidders, because the price will be higher and higher, right? So basically we have a numerical code, so give us any value distribution, any parameters, then we can tell you what's the equilibrium Honolulu auction was equilibrium in a Dutch auction, what are the expected utilities and everything. This can be done numerically, and we have some predictions. Okay, so what are the predictions? And it's almost 2, but we started 5 minutes late. Can I end 5 minutes?
Sorry.
So what are the predictions? The auctioneer, sorry. The bidder and auctioneer delay costs account for, but basically, like when we ran the experiments, and this was actually this is my, I think, 3rd paper that has experiments in it, but this is the first paper in which I did experiments. Like for the other 2 papers, basically my co-authors did everything. So for the first time, I actually like ran half of the experiments with my PhD students. So this was fun. So basically in the experiment, we expect that all 3 behavior can be obtained, and that will be let's skip that. And the other one is like we expect that there is going to be value efficiency. So that, as I told you, in this setup with time cost, the social value maximization and value efficiency are 2 different things, right? But in a symmetric equilibrium, we expect at least the values to be like the highest bidder will be winning the item. And so we have no dominance of Honolulu over Dutch or Dutch over Honolulu. Even from the numerical code, what we tend to observe is that there is an additional benefit of Honolulu auctions over Dutch auctions when we have small number of bidders, and when we have high number of bidders, this disadvantage goes away, and actually Dutch can become better. So this is like from the numerical graphs we can get that, and I'm going to skip many things in the experimental results. These are all the So I'm going to just like what are the main results in the experiment? We first of all see that value efficiency is 95% or okay, just a second. Very quickly, I need to also tell you that we have 4 treatments. And 4 treatments are dependent on 2 specifications. One of them, whether we have low number of bidders or high number of bidders. Low number of bidders was 2 bidders, high number of bidders was 5 bidders. And we have a treatment of low time cost and high time cost. So we actually fixed time cost of the auctioneer. We didn't want to make this 8, but we had low time cost to the bidder and the high time cost to the bidder. So we have 2H, 5H, 2L, and 5L treatments. And in all these treatments, the value efficiency is very high, 95%. So it's like efficiency is obtained also in the experiment. And the duration is a little bit different. So like in terms of duration, we actually observed that Honolulu took more than expected time. And Dutch also took a little bit less, because basically like in many auction experiments, especially in first price and Dutch kind of experiments, you actually tend to see overbidding, right? We also saw overbidding. So that kind of decreased the time and increased the utility to the auctioneer. So like in a nutshell, basically there are other things like I had, I think like 9 slides or something, 3, 4, 5, 6, 7, 8, 7 months, but there is no way I can go through. You are welcome to read the paper and give me comments. But basically, the main takeaways were that we were like that. There is like the average, although there are equilibrium. There is more weighting and more time than the equilibrium predictions. Still, on average, Honolulu auction was faster. Okay, but since there is some overbidding in Dutch auctions, we had in some treatments expected that the Honolulu auction would perform better in terms of the auctioneer's utility, but it didn't perform as good. But this could be also like related to bidders' inexperience. For instance, like there is a valid question whether this similar auction, if this is done with the experience, the fish auction participant in Sydney fish market, they may have, behave differently. There are.
So in the case of just two bidders, it seems English auction may run faster than the Dutch auction.
Yeah. So like basically for the two bidders case, we definitely expected like a huge advantage of Honolulu auction, because Honolulu auction's optimal starting price was determined to minimize and it's like slightly like it is faster, but in terms of auctioneer's utility, it did not result in significant gains because of some deviations from the equilibrium behavior. Yeah, that's all I want to say.
I think, historically, when do they start? Like Honolulu was, I don't know which one is older, but do you have some document why they start this program?
Okay, so we asked this question, like in Honolulu, and they say that they followed like the Tokyo fish market, but it's not correct, which is not correct because Tokyo actually uses English. And the Sydney fish auctions, I think it has been in effect for like 30 years or so. So I don't think it is as old as Tokyo one. And I think they wanted to like they focus on basically this premium fish, and then they want to give some like extra they make a mistake, for instance, right? So they want to give the opportunity to correct themselves. So I think their story was something like that. I don't think like when we talked to them, they did not say that we decided to use this auction because we saw that this was used in somewhere.
I see.
Yeah.
But they neither mention about time.
So they say that the time is very important for them, and this is like a time free. So like they actually explicitly say that this is done for time saving.
I see.
Yeah.
So I'm very aware that in other settings like spectrum auction, time is oftentimes the sort of concern. I wonder if these ideas of payment time have been incorporated in these other environments as well.
No, as far as I know, like there is this Kwasnica and Katak paper that like looks at more like here in our model, and also in our experiment, we incorporate these time costs directly into the utility function. But I think the Katak and Kwasnica paper, they look at like basically not in terms of the utility, like how much the payment they will get, but in terms of how slow the clock is, actually has an effect on people's behavior. Like the clock goes like this or like this, and then even like intrinsically, they have some kind of preference change, and they like have a simple model with like the time costs with different speeds of the time, but their model is different. That's the only paper that I'm aware of who actually consider time cost in auctions. I'm not aware of any spectrum auction papers that consider time cost. But spectrum auctions, I thought that I'm not that familiar with it, but it actually like it takes in weeks and stuff, right? So like they are given days to respond and go back and forth. So I'm not sure if this is best, but
Yeah, the only thing is that as far as I know, they kind of worry about it in practice, but probably not so much in theory, honestly.
Yeah,
and then, like you said, it takes a very long time, but especially because it takes so much such a long time, they want to have an auction that ends in the result.
Yeah, I see. Right.
So,
Yeah.
I thought that this could be very relevant.
Yeah.
So.
Anybody else?
Okay, so I guess that's some probably we have more questions, but then without actually checking his availability, I think he will available.
Yeah, so I'm meeting with you at 2:30, so, and I will be here like maybe till around 4, so if you wanna stop by, just let me know.
Sounds good, thank you. Now I got the permission, so let's thank again.